And welcome to this particular lecture where we're going to go over the physics involved with different geometric spaces. And this is really the meat and potatoes lecture for this course. Every other lecture that we've had in this course has been a building block foundation to get us here to make sure that you can understand these concepts as we go through them. And then, so with that being said, let's dive into this. And then, so the bottom line is what we're going to be looking at and examining here is we're going to be looking at physics throughout these different spaces. And then, so we've talked about geometric spaces throughout this course, specifically spherical spaces, Euclidean, hyperbolic, and fractal. And those are going to be the four spaces that we're going to look at within this. And within this, we're going to look at how physics operates within these different spaces and these different environments. Specifically, we're going to be looking at entropy, variance, and temperature, which are major parts of physics, right? And then so second law of thermodynamics says that entropy is going to go down over time and that entropy can be impacted by temperature very specifically. And then so we're going to examine some of these elements and like the laws of thermodynamics as we go through this particular lecture and this particular notebook. And so the very first thing that we're going to look at is we're going to look at entropy across fractal dimensions and how essentially variance, amplitude, and entropy operate across different fractal dimensions. And then we're going to be utilizing the Schrodinger equation for all of this, right? So essentially, we're extending out the Schrodinger equation. And then so in this instance, we extend the Schrodinger equation to fractal space in our first experiment. And then what we see is a rather interesting experiment to me in this instance. We shouldn't be seeing, to me, this variance, this peak amplitude, and this entropy, like it shouldn't be steady over time. It's an interesting result, right? And then so again, we're looking at fractal spaces in this instance, and then we're looking at fractal dimensions. So dimensions like one, in this instance, between 1.1 and 2.5. And then so we're looking at dimension 1.1, 1.5, 2.0, and dimension 2.5. And what we can see is that in this space, they all operate uniform, which is very unexpected. Uniform variance, uniform peak amplitude, and uniform entropy. This operates outside of the laws of relativistic physics. So this operates within the bounds of quantum physics, but not within relativistic physics. And so, next experiment that we go down to is, in this instance, we essentially want to break this down more, right? And then so let's prove this out because this is kind of interesting results, right? So again, just more math. Again, we're extending out the Schrodinger equation. So all of this is utilizing the Schrodinger equation. And then in this instance, we're just double checking our math. We're doing the math in a different instance, and then we're checking all of the different variables that we can, right? And then so we're just plugging in all of the math into our environment, setting up our fractal dimensions, and setting up this experiment to test variance, peak amplitude, and entropy. And again, we're not injecting any of these into the environment. We're measuring these in the environment. These are all natural things that occur because of physics. And then so there's variance in an environment because of physics. There's entropy in an environment because of physics. And we can see that that's true within these environments. We have an entropy close to 5 and a variance slightly above 2. But what is unique within this fractal environment is that these aren't moving. They're steady in this instance, which is again, it's not. It goes against the laws of relativistic physics for this to be happening, but we're dealing with imaginary spaces and with an imaginary fractal space. So, I mean, we're not dealing with a physical space, right? So that can be expected within that. So, next experiment then is let's take another look at the laws of physics within this fractal space, and then so. If I apply, let's say, like the laws of physics to hyperbolic space, I can get very clear and I know what the reactions are going to be, especially if I put agents in there. So if I put agents in there over time, what's going to happen in hyperbolic space is that they're going to start clustering together. They're going to want to get closer and closer to go and closer together over time. And I can prove that out. I can prove that out mathematically, etc. Right? In Euclidean space, they're going to want to disperse evenly. So we'll notice an even dispersion and an even dispersion over time, like not random but even. Right? So just out, like just even disbursement. But so what we see within this space when we look at this in our fractal space here, so we're measuring two things. We're measuring the entropy of this fractal space and the agent distribution. And then so here's our first agent distribution, second agent distribution, third agent distribution, fourth agent distribution, fifth agent distribution. And then so just measuring here, let's take a look and focus at these five, right? 1, 2, 3, 4, 5. And just going back and forth, up and over them again, right, a few times. So essentially what I can tell you is there's no discernible pattern within this, which is very odd, right? They're not clustering and they're not distributing evenly. They're operating under like chaos theory, essentially. And there is no predictable, it is literally no predictable pattern. It is not a discrete pattern. This is not a discrete environment or a discrete reaction that we're looking at within this environment, which is, again, odd. I wouldn't expect this in a hyperbolic environment. I wouldn't expect this in a physical environment. I wouldn't expect this in Euclidean, spherical, etc. So it's odd that this is happening in our fractal environment, looking at dimensions, again, between dimensions 1.10 and 2.5, very specifically. And then so let's look at entropy in this, right? Okay, our agents act weird. Now, what about, I mean, if you know anything about entropy, these entropy graphs are kind of the weirdest thing that you'll ever see in your life, right? Like, entropy shouldn't be doing this. It shouldn't be fluctuating randomly over time. It's kind of very, very peculiar and very interesting. So within this fractal space, we have variance and entropy operating in ways that we would expect within quantum space, and then very specifically our agents operate in ways that we would expect within quantum space, and our entropy over time operates in ways that we would expect in quantum space. So again, this is measuring dimensions, fractal dimensions 1.10 to 2.5. Absolutely none of this gets into proven mathematics. So I'm just going to leave this here as this experiment. This is the reason why I have this whole entire course is free, right? Like I want to highlight and show these things as much as possible. So let's dive further into the physics of this equation that we're looking at here. And then so we looked at some kind of crazy things if you know what we're looking at mathematically. So let's dive into, and again, so let's double check it all, right? Because let's make sure, yep, okay, that's exactly what's going on. Steady entropy, steady information over time. About a different test. Let's make sure that we're not crazy, right? Okay, so we know because of the laws of thermodynamics that if we increase the temperature, right? If we adjust temperature, entropy will adjust according to temperature. That's the laws of thermodynamics, right? And then so here's our experiment. We, in this fractal space, in this fractal dimension space, this fractal dimension is less than 2.5, we are fluctuating our temperature, but our entropy increases over time, which is not what should be happening according to the laws of relativistic physics. Again, according to the laws of quantum physics, this is all good. this can be happening, right? I'll let you piece this together. But so let's go through and let's look at essentially. So we've noticed something interesting here, right? We've examined and we have isolated fractal dimensions 1.10 to 2.5, and then so. Let's look at this, right? So 1.10 to 2.5, there we go. And then let's start experimenting around that. And then let's put in different experiments, right? So let's measure, right? Let's make sure that we're not looking at bad data here. Maybe there's something messed up with these experiments. So let's look at variance in Euclidean space. Yeah, variance increases in Euclidean space. That's expected, right? And variance increases over time. And then so hyperbolic space, same thing. We have variance increase over time, exactly as expected. Spherical, same thing. Fractal. different. It's not operating exactly as we would expect in this instance. And then so let's compare this variance between these. Interesting things start to appear here. What we can see is that there is actually a difference in variance across different geometries. This shouldn't be happening according to the laws of relativistic physics. But what we can see here is that we have different variance in spherical space as opposed to hyperbolic space, as opposed to Euclidean space, as opposed to fractal space. In fractal space, we've got almost no variance according to like when we put these in comparison, like fractal space is pretty much flat with regards towards its variance. And then highlighting that and pointing that out, it's I would say that fractal space and spherical space are kind of maybe perhaps two different ends of the spectrum that we're looking at within how this is breaking down and looks at, right? Like fractal space would be the very small, and then spherical space would perhaps be the very big. Maybe this is putting some strings together for you. If not, let's go forward. So we go through. And we can look at this. Let's look at peak amplitudes, and then so peak amplitudes of the wave function, right? And then we can see like this data checks out. But it's interesting here. Very specifically, we've got variance in Euclidean space, like a ton of variance in Euclidean space. But when it comes to like the wave function, these time steps, what we can see is that it's actually within a fractal space, it's lining up, interestingly enough, and we'll come back to that. Right? And then so when we come here to this comparison of entropy across geometries, same thing. We can see that there's a major difference, and this is lining up with that data. That the variance data is showing this exact same thing, right? Where we have a lot less entropy in spherical space, and it shoots down in spherical space, whereas it's a lot more stable across fractal space and across fractal geometries. So we're seeing some very interesting experiments here, right? And then so very last thing that we'll look at within this is, so then if variance is different and we can see that fractal space happens to be kind of like let's call it a dampener. What would happen to the quantum wave function and quantum wave collapse in fractal space as opposed to hyperbolic or spherical or Euclidean space? Well, this is interesting because there's no quantum wave collapse here, is what you're seeing here. So I'm just going to highlight that for a second. We'll come back there, right? And then so so I mean that's an experiment, which we'll come back to. But let's come back here and then let's make sure okay, we just saw a crazy experiment. So again, let's double check the work in all of this, right? So let's double check and make sure that this is all actually checking out. So let's again look at variance across geometries, as we can see, and as expected now in this instance, we see that there's a difference in variance between Euclidean geometry and especially spherical and hyperbolic geometry. So we're just measuring those three because if we're just measuring those three, because they would mess up our graph if we put fractal in there. Just honestly, it would end up like this, right? And then so what we can see here is, so let's do this across fractal dimensions, but let's play around with this. Let's do 1.5, 2 fractal dimensions, and 2.5 fractal dimensions. Interesting here. What we're noticing here is that essentially the difference between 2 fractal dimensions and 2.5 fractal dimensions is essentially 2 different universes. They operate, there's different laws of physics occurring in fractal dimension 2.0 as opposed to fractal dimension 2.5. That's what we're looking at here with this data. I'm not saying that's what the data is showing, right? And then so let's go through here. Let's look at that wave function again across different amplitudes and the amplitude of the wave function across different spaces. And again, we're teasing out that the wave function, the amplitude of the wave function, it can go higher in spherical space than any other space. There is a difference between these spaces with regards towards the quantum wave function and the amplitude of the wave function. So there's different geometries and different physics going on within these environments. And then same thing here. We notice, and we're just comparing these fractal geometries alone to fractal geometry 2.5 compared to 2. It's again two different worlds, like majorly, right? Like there's again no wave collapse in fractal dimension 2.0, and then collapse, extreme collapse, and fractal dimension 2.5. And then when we look at entropy across geometries, same thing, right? We're noticing and teasing out this difference across the spherical geometry, and then very specifically at fractal dimension 2.5, there's a very specific break. Highlighting it again, I can't point this out enough. Fractal dimension 2.0 is a different universe than fractal dimension 2.5. You're looking at it here. And then so where does that difference start to occur then, right? That's what I want to figure out next is, okay, so 2.5, fractal dimension 2.5 is off the charts different than 2.0. But what about 2.4 compared to 2.5? Interesting. That's where we start to see the break right around fractal dimension 2.4. We start to see a bend, like everything is like, so fractal dimension 2.0 is actually very stable is what this data is showing at. I mean, it's stable with regards towards like quantum mechanics. It's quantumly stable in fractal dimension 2.0. Once we get to fractal dimension 2.4, it starts to break, starts to crack a little bit. Fractal dimension 2.5, it's off the chart, it's cracked, like quantum wave collapse, right? And then we can see this again, just so then the last experiment. So we've at this point proven out on the fractal end of the equation, right? And again, we're utilizing the Schrodinger equation for all this, we've extended the Schrodinger equation out at this point fully throughout fractal space. Let's do the same thing with spherical space, right? So is there a difference in entropy over time between spherical dimension 1 and spherical dimension 10? So fractal dimensions, we're dealing with these small dimensions, right? Like 1.1 to 2.5 in that realm. Whereas spherical dimensions, we're dealing like dimensions over 5. And so like fractal dimension 10, right? And we can see the massive difference between spherical difference 1 and spherical difference 10. That like there's actually more there's less entropy in spherical dimension 10 than exists in spherical dimension 1. Very interesting. The laws of physics are different in spherical dimension 10 than they are in spherical dimension 1. And then what we can see, so then let's play around with this, and then what if we blend these geometries together? Like, can we notice differences there? And then yes, absolutely. And then so what we can see is that by playing around with the different geometries and then creating hybrid geometries, the entropy in this instance functions very differently in these different universes. So these are three very different universes. Hybrid universe 0.5 compared to hybrid universe 0.7 compared to hybrid universe 0.3 are three different universes. Same thing with training loss, which is very interesting, right? So we can see that our training loss across fractal dimensions is what we're looking at here. And then so by increasing the fractal dimensions up to 2.5, like so between 1.0 and fractal dimension and 1.0 and 2.0 and then 2.5, like there's a big difference here. I would want to train loss and I'd want to train loss for a very small amount of epochs in fractal dimension 2.5. This looks awesome, right? Like it's just like, okay, cool. Fractal dimension 2.5 is better for training in this instance than fractal dimension 1.0, and that's what I tease out of this. And then so kind of interesting as well there, highlighting that, and then graphing this out over time, we can see this same thing. So let's do this for spherical. Let's extend it out to spherical space. So then we'll go out to like dimensions like 50. So we'll go like 1, 5, and 50. And we can see this does have an impact on the training as well, and a unique training with essentially with dimension 5 being like an outlier within this. Like dimension 5 very specifically taking longer to train than the other dimensions. I don't know why. I'm just highlighting that and showing what this data is showing here, right? But so highlighting that it impacts both fractal space and spherical space. I focus on spherical space because that's where we're getting the biggest impacts within this, right? We're showing the most variance within fractal space below 2.5 dimensions, and I can very specifically at this point measure that fractal dimensional difference between fractal dimension 2.4 and 2.5, and explicit within this data. And then so this shows you and hopefully proves to you that the physics involved in the geometry of these spaces that you're training your neural networks in makes a big difference within it. It can make a night and day difference. It can impact every single aspect of your model. And so if you're not accounting for this, you're missing out on a lever and a big lever that you could be pulling and that could be necessary for your internal AI functions. So I hope that you've liked this course and I look forward to seeing you in future courses. Thank you very much.